Hello guys, how are you doing? I'm gonna start the class again or the lecture by hello guys. Today I wanna do something different that I have done in the past. What I want to do is a problem that is a fairly common problem in every book. Let me switch this here. Docam, perfect. This is a problem, you see? This problem is a really common problem, and I have found that a lot of students have problems with the problem, has issues with this problem when they try to solve it because they don't understand how these constants work. And as I say in a previous video, they say springs and they start like, oh, springs, oh my god, I'm so scared, I have nightmares with the springs. And you don't have to have nightmares with the springs. You can have another type of nightmares if you want to, but don't, Freddy Krueger for example, but don't have nightmares with the springs. So usually when you have this situation, there are two possibilities that you can be asked for, and I copy both here. Either you have the setup like that and you have questions like determine the stretch in the springs AC, this spring here, AC and AB, which you already have the constants, and you already have also this constant in this particular problem was 40, I guess, I think, I don't remember, and I don't care because I'm not gonna solve that problem. So if you thought I was gonna solve this problem, you can stop it. I'm not gonna solve the problem, but I'm gonna explain you something more important than solving the problem. So you go here and it says that the springs are shown in the equilibrium position, meaning that you have all the distances and everything else, and what you have to find is what is the stretching in these springs. How do you do that? Well, you solve for the geometry, you solve for summation of forces here around this point, you do the free body diagram, you can calculate the angles. Remember, this is the angles for equilibrium, and then you can calculate the force because you have the force and you have the constant. You can calculate how much the spring was stretched, period. That's the way you do that. Now this other one, it says the on a stretch length of the spring AB, you only have this on a stretch length is 3 meters, and if the block is held in equilibrium position, this one, calculate the mass. Is kind of the same problem, you just work backwards in that problem, but you need the original stretch length here so you can calculate the other position later. Also, that's my cell phone, by the way. That's really good, but what I want you to do right now is not to solve that problem. What I want you to do right now is make a model of that problem, because the model is, I don't know about you, but I learn a lot by seeing things, by doing things. So what I want you to do is try and come out with that model. Let me show you the model again. Here. And the first thing that you're gonna say, where do I get springs? Where do I get pins? How do I do that? Well, I'm gonna give you just a little tip. You can use springs and you can buy springs, and there are really, where are my office? I'm gonna show you my office because my office is a really nice mess. That is my mess. You can find these little devices. They are like a buck something, $1 something, and those are spring scales, and your problem is solved. But then you have to buy these and you have to get these. If you want just to build a model for your own use, you can build something more simplified with different type of springs. Rubber bands. Rubber bands are in the elastic range, but then you're gonna ask, oh, how do I modify the constant? Well, you put 2 rubber bands, then you have double of the constant, theoretically. And I'm saying theoretically because that's probably not gonna happen, and I shouldn't be telling you what the errors are gonna be. I should just let you figure the errors by yourself, but I'm gonna tell you what happened here. So how do you calculate the spring constant? I explain this to my static students. So you just apply the Hooke's law, which you know because you learned that from high school, and you learned that in physics and probably in calc also. F equal kx, F force, K the spring constant, which is also called stiffness, and is no other thing than the slope in that force elongation line or equation. And you just have to hold this in a position, hang away from there, and measure the elongation. Theoretically, that's sufficient, and I say theoretically. Let me turn to this board that I prepare, or we prepare, because there's a person here helping me with this. But let's turn to that board because that board is gonna help me to do the explanation. Okay, as you can see here, I have a. Oh, that's good. You're not seeing me. No. I'm the protagonist, so you have to see me. Well, kind of. I put here 1, 2, and 3 rubber bands hanging from here, and I'm gonna just hang some weight. And you say, okay, I don't have a weight. Of course you have weights. You have scales at home, and even if you don't have scales at home, I don't know. There are certain things that you know the weight or the very very approximate nice weight, which is, for example, a bottle of water, and you know that's a pound. So you can start thinking of those quantities. Now be careful with something, because the way you do this is that first you put your rubber band like that, and you draw the baseline for that. That's gonna be the initial length, and then you get a known weight, and you hang that known weight from that, and then you measure that distance. How do you measure that distance? With the ruler. I measure that in centimeters. I mark the point there, and this is approximately like 4.5 centimeters or so for that one. Now be really careful, because I'm pretty sure that if you just get a bunch of rubber bands and you start trying the rubber bands, you're gonna mess up. Why? I'm gonna show you. Look at that rubber band over there. I'm gonna put another rubber band from the same box here. Now look at the elongation. The elongation is like 1 point times the other one. So the first thing, the other one was 4.5, and this one up to this point is almost 8. So what you should do from the beginning is just selecting a bunch of rubber bands with similar elongations, and it's easy to do, but it's highly necessary. So you do that for the 3 of them, and then you put the 2 rubber bands, which I already tried, and then you put the second one, and then you mark a point, and then you do it. As you are adding rubber bands, it's going to be more difficult, so you can add more weight to that, and you have a better solution for this one. For example, I already did the calculations and I measured them. So for the second rubber band, this here, if you see, coincide kind of almost too scary crazy with the first one, but the reason is because I already selected the same type of rubber bands within the bag. So it's the same elongation for double weight with 2 rubber bands, and then you do the same thing with different weights and with different situations, and then you do the same thing with 3 rubber bands. And whenever you have the 3 rubber bands here and you measure it, this is like 2 point. You have to mark the points exactly there. You are supposed to put the label over there, a bubble label or something. But this is like 2.8, 2.7, 2.8, something like that for 3 rubber bands. And you can do the same thing for different weights. So you can put one weight that you know, add another weight, etc. In my case, I'm adding these because I had those. You don't have to have these. Each one of these is 5 newtons. So I'm adding 2 of 5 newtons. And then I have 2 extra more that I'm adding, or 1 extra more of 2 newtons. Okay, let me go back to the, no, let me come back here. So once you have the rubber bands, the idea is to reproduce the experiment that we had before. So I get something like this. This is just a ring from a keychain, and that's gonna be the bottom part of that, where I'm gonna hang the weight in that part. And then I have these 2 rubber bands are gonna simulate one of the springs in one direction. Let me try to be quick here. Fast. Just be sure also you don't damage your springs by doing that. And I'm showing this at this level because I always receive concerns and, oh, I have to spend a lot of money by doing this. No, you don't have to spend a lot of money. Rubber bands are everywhere. So I had the other one. Now, if you remember the problem, this is just a hook here. You can use paper clips if the paper clips are sufficiently strong to hold it. You put 1 rubber band here, you put 2 rubber bands at this point, 2 of them, and then you're gonna hang the weight at this point. When you hang the weight here, there you go. Be sure that this is not touching directly the board that you are putting there, because otherwise it's going to be friction here. So it has to be vertical, but it has to be somehow hanging there. You see the shape this is exactly the same shape that you saw in the problem, kind of, because I realized there is a problem with that drawing, but it doesn't matter. This is what I want you to do. Once you do that, then you're gonna come here and measure the physical distances for the weight that you know and the spring constant that you should know. Now, how do you calculate the spring constants? Let me go back here and let me show you how to calculate the spring constants really easy. So if you come here, okay, you can go and I'm just gonna show you really quick for this example how to do it. What are you looking for?
Black.
There you go. Or you can use this if you want to. Okay, so I'm gonna show you the results that I got for the Spring 2 PPT plus webcam. Okay, perfect. Here I have my Excel page here, and this is the stretching that I measure for the Spring 2, which is not a spring, you know that, right? It's just 2 rubber bands. So for a force of 5 Newton, I got a stretching of 2.3 centimeters. For a force of 7 Newton, I got 3.2 centimeters, and for a force of 10 newtons, I got 4.4 centimeters. You get these here, you mark them in Excel, you say insert, we're gonna go to the scatter plot, and I want to select these, which are only points markers, because the points are not gonna coincide, and that's good, that's normal. That means that the material is not perfect. But then what you're gonna do, you're gonna add a trend line here, trend line, and the trend line that you're adding, you're saying to show and display I'm sorry, the equation on the chart. If you want to, you can also do it by hand and draw the more approximate line that you can do it like this. So you don't have to do it exactly just like that, really quick, and do the drawing, and we put the measurements later. So I say that you can also fit it by hand and measure the slope. Now remember that look at the chart that you have. You see, this is the chart, and this here is the slope. Now forget about this term, because this term I'm starting not from 0, even though it's really close to 0. I didn't start it from 0 because when I did this experiment, I started from a baseline. This baseline that you see, well, you don't see it here, but you see it over there. Basically, the baseline that I'm starting, it was just to keep the rubber band, to keep it for a first position stretch, and that's why the y-intercept will represent the original deformation. Forget about that, but think of this slope. This slope here, it's gonna tell you actually what is the force, which is y. This is the force divided by the elongation. So you have force divided by elongation. When you plot the force, the y-axis divided by the elongation here, is going to give you the spring constant, which is for the Spring 2 about 2.4. Now I did the same thing for the other springs, and I'm gonna show you what the results are. Results are for the other spring. Switch to DocCam plus webcam here. These are the results that I got for the 3 springs. Actually, this is a Spring 1. This is a Spring 1. I put 2 times a Spring 1. Oh, that's so smart. But I just show you a Spring 2. So a Spring 2. I'm doing this live, so guys, errors happen in the best families. So let me see, what is this? A Spring 2. You are the one that I need. Copy Spring 2. Come back here. You know, this is gonna show you that this is just a production that is on, not pre-recorded, not edited, not anything. And then I'm gonna go here and I'm gonna paste it here. Voila, there you go. And I'm gonna print the new sheet. File, print, and print the current slide. There you go, print. And now we have it here. Okay, rewind that, forget about that. This is the one. Spring 1, Spring 2, Spring 3. Look at the constant. This is the constant for the Spring 1, this is the constant for the Spring 2, and this is the constant for the Spring 3. This is kind of 1.14. This is 2.39, and this is 3.58. Look at these values. We are basically trying to work with a value, a constant of 1.2 for the first one, 2.4 for the second one, and 3.6 for the third one. So once we have that, I'm going to show you the dimensions in the drawing that we were preparing here on only webcam. There you go. This is the way it looks like. So what we are doing here now is, where's the marker? Any marker here? You can basically take this out because the cable, I'm gonna put the cable in, yeah, same color, doesn't matter. So the cable should come somewhere here and somewhere here, and this is the ring here, and then you have the other cable coming from here. Now if you take this out and you take that out, you have the problem. You see, this is the problem. These are the real measurements, and you have here 10 Newton. So you have 10 Newton of force over there, and then you have the dimensions here. Now what you do, and what you can do to see if what you did was correct, is you come back to your original drawing, which I have somewhere in this mess. I have here. Let me show you again. You have it here, and then this is the problem that I showed you before, but there are no values here. And then you go and you proceed. What do you proceed? You say, oh, this distance here, experimental distance is 14 centimeters. This other distance is 8 centimeters. This constant, I say that for this spring was only one rubber band, so that constant was 1.2. Remember the units. The units are Newton per centimeter because that's what I use. This is 2.4 Newton per centimeter, and this is 3.6 Newton per centimeters. This weight here is 10 Newton. The vertical distance that I got from my result here, from here to here, is 10.5 centimeters. And now you go and solve this. Are you gonna have errors? Yes. Are you gonna have discrepancies between what the theory should say and the practice, the practical experiment that we are doing is? Yes, of course, and those are expected. But you know something? That's what experimentation is about. These rubber bands, as I show you, they are different. They have different thickness, different stiffness, different everything. If you hang something from this rubber band and you overstretch it, forget it. It went to the plastic range. So, or the elastoplastic, the plastic range. It's gonna go back, and you're gonna say, oh, it's the same one. No, it's not the same one. You have residual deformation there. And if you go to mechanics of materials after this, you will learn what is happening. Now, what I expect you to do, go through that problem and solve that problem in the way that I told you, and try to come out with some results to see if they are. You can just forget about this weight for now and say, oh, if I have this situation like that, what is the original, what is the weight that is here? And you can have also the unstretched length, because that was one of the values. How much is the length of one of these rubber bands, original length? Measure it there, please. The original length, original spring
9.5.
What?
9.5.
9.5
centimeters.
9.5, 9.4 centimeters, somewhere around that point. Okay, if this is the original length of the springs, then you can come with the solution and try to solve that problem. Do it, because you have no idea how much that can help you to understand the whole process. And solving a problem in paper, yeah, nice. Seeing it like that and trying to solve it, priceless. For everything else, you know what card you use. See you next lecture, guys. I hope you like